I'm delighted to be here, and I wanted to thank John and others for inviting me. Today I was going to talk about a cognitive architecture I've worked on for about a decade, and my colleagues. It's called MIDCA, and we'll look in particular at the interface between cognition and the world, similar to what has been already discussed, and also look a little bit about cognition's interface to metacognition. Let's see. Oh, page does not want to. There we go. Okay, so you can think of cognition as having three levels, one of which, the ground level, is the interaction with the environment, both where actions are executed and where we receive stimuli in terms of percepts. The object level you can think about as where reasoning occurs, both problem solving to solve goals or comprehension to not just input the percepts, but interpret it with respect to your goals and plans. And then there is another level called the meta level, which is similar to action perception, but instead of acting in the world and perceiving the world, you want to control your reasoning and have some kind of a trace or input about what your reasoning is doing in an explicit way, so that just like you would have models of the world, you could have models of the self. So our architecture, MIDCA, is the Metacognitive Integrated Dual Cycle Architecture, and it has two similar action perception cycles. One I mentioned, which interacts with the world. The other interacts with cognition. The details here might not be visible in a way, so let's focus on the orange, or the cognitive loop. There are 6 main phases, and they're reproduced also at the metacognitive level. But you can perceive the world through percepts, and then you extract from those percepts a relational state and a first order logic. You then interpret the state of the world with respect to the plans, pi, that you have currently in play, and evaluate that with respect to your goals. Now, interpretation has it's a little different in our architecture. The idea is one of the key aspects of interpretation is to detect problems in the world when our observations differ from our expectations, to explain those problems in a causal fashion, what caused the problem to occur, and then to generate new goals to remove that cause and hence solve the problem. So G7, a new goal, can be generated from the interpretation comprehension process. Now, given a set of goals, you want to be able to intend, will select from your agenda of goals a subset of those goals, G sub C, and then plan will achieve or come up with some sequence of actions that would achieve, if executed, the goals, and then act would iterate and execute those actions one at a time, looping through the cycle as you do. So this is, I think, other than the interpret phase, similar to many architectures out there. And the plan phase, I might mention, we do have in our architecture, I think, 4 different planners, 5 actually, different planners that can be used as modules in the planning process to generate plans to achieve goals. So, well, backing up, I did want to mention that it's the interaction with the world and cognition's interaction with metacognition, which is the focus today. The outline of this talk is that we will examine in some detail these 2 interfaces. However, given the lack of time, we've cut it down a little bit. I'll probably focus more on the interface to the environment and less on the interface to metacognition, but hopefully we'll be able to cover both in some detail and conclude with a few remarks. So this is a different way to look at the interfaces here. There's a Cognition can interface with the world through real robots using ROS, the robot operating system, which is not quite an operating system, it's a middleware, but a distributed middleware. There's also an interface to Moose IVP, which was developed at MIT for modeling and controlling surface vessels and underwater naval vessels, unmanned vessels. And then we do have a standard simulator. There's a gazebo simulator that's also available, but today I'll talk and focus mainly on ROS in terms of the interface to the world. We'll also spend some time looking at the interface to metacognition. What are the items that you would represent in a trace of your cognition, and then how is it that you would control cognition in the upper interface. So first, I can mention that there is a file that can be generated for MIDCA when creating a new domain that would describe the types of objects and the relationships between them in the world for a limited domain that you are developing. And then also it has an ability to define the operators and their mapping to low-level communication channels. So in ROS, this is done through a publish-subscribe architecture in which you have computational nodes that are communicated with through what they call topics. So here we can see for a simple blocks world, in using ROS, we can define blocks as a type entity, which is the root or the highest entity in an ontology. You can also say that blocks have attributes. Color is one. They also have XYZ coordinates. The attribute value colors could be in terms of red, green, and blue. This is a very simple world. X, Y, and Z are integers. We have a couple relations that are defined here. On is between two blocks, relationship between two blocks, one being on the other. And the relation clear, which is a unary predicate that would note that there's no block on top of a current block, or that it's clear. The actions here are the 4 standard actions: pick up, put down, stack, and unstack. And you can divide, for instance, unstack in terms of moving the arm to a location, gripping it, and then raising the arm along the Z-axis. So by creating this file, it actually, there's some code that will take and generate stubs for the object detection code you have, and it will create stubs for perception action handlers, so that it allows the developer to then, for a particular domain, to fill in the details. So looking a little closer, again, in the blocks world, actions in terms of PDDL operators or planning operators. It's plan definition. Let me see the plan domain definition language. And we're using PDDL 2.1. The perceptions are in terms of logical predicates in a first order logical syntax. And these are mapped through ROS topics to particular computational nodes. Here we can see a particular block 1, which is red at a certain position. The green one is at another, and you want to infer from that which block is on the other, and then the unstacked action uses particular topics that go to the nodes that control the effectors on a robot. Looking a little closer, there's a sensor handler that's interacts with ROS, and as object positions are detected, they're put on a visual buffer, and then for instance, their IDs and attributes are put in there. The perceive phase in MIDCA then has to extract from those, for instance, block 1 being at a certain location being red. It would then go through all these objects and their attributes and extract the predicates in the domain. And I will come back to it, but that can be computationally quite expensive. Action is fairly straightforward too. Here we would move to the particular location for the red block, grip it and raise it. So those unstack is mapped to 3 lower level actions in ROS for the particular robot that you would be operating with. For us, it's a Baxter robot. The act phase then watches for feedback to know when that command is finished and unstack is complete. The problem with this is there is too much unnecessary computation. You're constantly having to infer all possible relations in a world, and you could spend unnecessary time. So how to control that is an issue that I've had some students. Zora Dannauer did her PhD thesis on it a couple years ago. And the idea was to have to manage perception through plan and goal monitors. So goals have a reason for why you're trying to achieve a goal. If that reason changes, you might drop or modify the goal. Likewise, you have plans with certain steps in them. The operators give the preconditions for that. For instance, we're looking at a Baxter robot here that is going to stack red on green. For the pickup action, red must be clear. So you would want to actually monitor for that clear, because if somebody comes along and places something on that or changes the fact that red is clear, you won't be able to pick it up. You would need to insert steps to change that. And so planning allows specific monitors to be generated so that you focus on those relationships in the world that are important for actually executing your plans and achieving your goals. A very brief little video here just does that. Somebody comes along while the robot is actually planning, so it's been watching for that and other certain relationships in the world that is crucial for the correct plan execution. And so it inserts the unstack and the put down on the blue block, and then it can continue with the plan successfully achieving red on green. So this is just a very simple demonstration in a very sparse world, but in general, you need some way to manage the amount of percepts that you're trying to extract. Okay, so then we'll go on and we'll take a look at the second interface to metacognition and what we'll look at there. Like the previous cognitive cycle, there is a very similar cycle of 6 phases in the metacognitive cycle. Here we have monitor takes input of some trace of the cognitive processing. That is then interpreted and generates new goals if necessary. We'll have an example we'll talk about here soon. And you could evaluate the goals that you have, whether or not the goals have been achieved yet. Intent chooses a subset of the goals that you might have at the meta level, and plan creates some kind of a plan to make a change in cognition, and then the controller executes those. So what we might change is a couple different things that, for us, the key to, or the basis for getting things done in Christian's sense is goals. So if one way to control cognition is to actually change the priority on your goals or change the goals themselves, we also would want to learn better action models in the world to improve our problem solving and the execution of the plans that we have. Or we could prioritize the cognitive processes that we have. There are a number of different ways. So let's look at this in a little bit of a detail. Essentially, we can think of an execution trace as just a sequence of memory snapshots that occurred before and after each of the cognitive phases that are executed, or even within a particular cognitive phase. So here we can see that there is some mental state before intent and some mental state that occurs after. So like the world, you have actions that change the world, and you have a state of the world and some action in the world that like picking up a block that will change the state and the predicates that you have. Here we have cognitive actions that likewise change our memory, current memory in a particular state. So there are, just like a system would have expectations about the world, for instance, a certain action is going to result in a certain change of state, we also want to have expectations about cognition itself. And we have formalized these in terms of a Boolean function over the segments of this mental trace. At the current time, the mental state is a vector of variables. For us, it's a 7-tuple. GCC, the current goal set, the current goal agenda, the plan pi, the world, the state of the world, any discrepancies that have occurred between your observations and your expectations at the lower level, explanation of those, and the current action that was just executed. And so we did mention that interpret is a 3-part process that looks to detect problems, explain the cause of any of these problems, and the generation of a goal from those explanations. And for instance, we could have the expectation if this memory snapshot 2, if it was there were discrepancies that had occurred, then we should be able to generate an explanation about what caused that discrepancy. If there was no explanation generated, then there's a metacognitive expectation failure. So I might also mention that there is a full metacognitive cycle after each phase looking for these violations of your metacognitive expectation. So for control, there are a number of ways that I mentioned that you could change your goals or the priorities on those goals. We could have control over the cognitive phases. For instance, we might substitute one planner for another planner if the current planner was not sufficiently generating optimal plans, for instance. I hate the word optimal, but satisficing plans. And we could also have to learn some action models or this PDDL model in terms of roles, preconditions, and effects, and other things are possible. I'll give one brief example and try to wrap up here. There's a domain that a master student recently created called Plant Protection Domain. It was actually developed at NRL originally, and we replicated it. Here we have some agent in a garden, which is the center white part of the cells. There could be invasive plants in there and then native plants. And we would have the goals to use herbicide on and destroy any of the invasive plants and preserve any of the native plants that are in the garden. So we might have our agent go to the invasive plant. I think I did this incorrectly. He should be at 2-4 and he would spray there, but he ends up killing not just the invasive plant, but he would kill the adjacent plant. And this is because there is an incorrect operator. The operator just has the effects that it will kill any plant that's in the spray, in the location that the spray is performed, but the actual operator should be that adjacent cells are also affected by the herbicide. In this case, from the examples that fail in execution of the plans, it wants to be able to learn a better operator. Here there's a goal expectation failure because this expectation just says that we want to, once a goal is achieved, or if it's achieved in the initial state, it should remain achieved unless we do something, or another agent that we observe does something to change that. Here, the goal to have the native plant preserved was already true in the initial state, but then that spray did create a discrepancy because it killed the native plant as well. So the agent has no explanation of how this occurs. So in the trace, there's a metacognitive expectation failure. It generates a goal, therefore, to learn the operator from the examples that it encounters. And it uses a relational learner called FOIL to perform this. Let's see, so I am not going to talk about the results in the second domain, but in the plant protection domain, there was a version. So again, for time, I have not been able to talk about what the rebel agent is, but it's actually an agent that, like the inner conflict, I think in Antonio's work, there's a conflict that it might see. It was given the goal to remove native plants, but when it sprays and there's adjacent, to remove invasive plants, but it might actually rebel against doing some goals when it identifies that there's going to be a conflict. In this work, we have increasingly more complex problems. It goes from one goal all the way up to 20 goals per scenario or trial. And the performance, when you have a single or two goals, is at 100% for all agents. But as they become more complex, the standard agent that does not rebel or does no learning performs worse, and the rebel agent next. But the learning agent, the one that can learn a better operator, using expectations in both cognition and metacognitive expectations, was able to perform best in this domain. So I think in conclusion, I just wanted to say that this is available in GitHub. It's an open source system. And we've been working on MIDCA for over a decade, as I had mentioned, but it's only recently that we've started to look at metacognition in some detail. We have put far more work that we had realized into the cognitive cycle, particularly in what we call goal reasoning or goal-driven autonomy, trying to imbue agents with an ability to actually recognize when things go wrong in the environment to generate their own goals. We've also ignored grounded cognition for a long time, but both have become of interest to us. We've talked a little bit about that today, and I think the future is interesting with a lot of preliminary work that we're hoping to mature. Thank you. I'll stop there and take questions.
Thank you so much, Michael, for a very interesting talk. The first question from Rami Bandri is that, would incorporating something like autobiographical memory enhance metacognition in any way?
Oh, to enhance metacognition. So that's interesting. So we've actually been interested in an episodic or autobiographical memory before, and I have not had a student to take that on. And I do think that, right, the knowledge of what we do is, and what occurs looking in the mirror, developing a model of the self, is about the body, as I think Antonio was talking about, but having knowledge about our own problem solving. Autobiographically, I knew when I was a student in calculus, as I learned new calculus problems, I did have a familiarity with those problem solving episodes, the mental problem solving episodes. I knew when I was on a right track, and I knew when I was lost in a problem, when I just did not have a clue, and it was very different. And so I think there's an aspect that would be important in autobiographical memory for metacognition. I have not worked in that, though.
Okay.
yet.
Excellent. So Bob Ray has a question, and he says, when a discrepancy arises, how does the system's metacognition interact with the rest of the cognitive loop? Does the agent continue, or does metacognition become the focus of the agent's processing until it resolves the discrepancy?
So there are two different types of expectations. There can be an expectation failure in the world where, so let me just say, there was that plant protection domain was a little bit more complicated than what I led on, but I did mention that there was this first expectation failure. I expect when I do the spray to kill any of the plants in the hex that I'm in, and not in the adjoining ones. So when I did mistakenly kill the plants that were adjacent to the hex that herbicide was put in, that was a normal expectation about the world and the way behavior and actions work. And it allowed the agent to do rebellion into the future. But when that same expectation failure, part of interpret, goes to the metacognitive loop, each time you do a phase, it jumps and does a whole cycle at the metacognitive level. It then looks and tries to explain if there was, well, first, it was not able to explain what happened in that discrepancy. So at the meta level, that was then a metacognitive expectation failure. And then it generates a learning goal, selects that goal, and comes up with a plan to achieve it by calling FOIL, essentially. So there are two different ways that expectations work. Not all normal expectation failures will result in anything of importance happening at the metacognitive level. It may or may not.
Okay, thank you. And a question from me is, so anytime you're dealing with simulations or robots, of course, you have to make particular assumptions. And so one of the problems that frequently happens is you have a perceptual failure or a motor failure. And so, for example, you might be looking at a block, but it suddenly turns into an elephant, right? Or it turns into something that you are not expecting given the current perceptual system. And there are various ways that roboticists and perceptual people deal with this. But for your system, if something like that happens, how do you deal with it? If you get basically an unexpected failure, either in perception or the motoric or something else. And so how do you actually tell those sort of differences apart from a goal reasoning problem?
Right. So I think this would be similar to the problem I've struggled with for a long time. That is, if something, let me do one instead of perceptual, I'll do one with an effector. Say I try to pick up a block and it drops. The problem could be that my gripper is broken, or the problem could be my model of pickup is broken. So I don't know necessarily whether or not I should have a learning goal to learn a better action model, or I should repair, so generate a goal in the world, an attainment goal to fix the broken gripper. Either could be true. The same, I think, is also true in perceptual problems. I don't know if my knowledge how to interpret certain percepts is wrong, or is it that I all of a sudden have fog that made it more difficult to see, or or actually some film over a sensor. And sometimes I think there are some heuristics that you can use to solve this, but I don't have a general solution. One is, for instance, on the when I observed the spray action to kill adjacent plants, it might have been that I could observe another agent that did that was in there killing some of the native plants. It just happened to be when I sprayed next to it and I observed them. Then I want to generate an attainment goal to stop that other agent, or in some way to force that not to happen in the future. Or if I don't directly observe something, I might think that I need to learn this spray action better. But there are certainly cases where it is hard to differentiate the need for a learning goal over the need for an attainment goal to change the world.